Hello and welcome to the next video. Today is one of my favorite topics, photoelectric effect. This is a very interesting topic to me, and this photoelectric effect, explanation of the photoelectric effect, revolutionized the study of quantum mechanics. So let us get going. What is photoelectric effect? It was observed that when light falls on a metal objects, these lights can, if it falls on metals, they can knock out the free electrons of the metals. Okay, so this process, the light interacts with matter and knocks out the electrons of the metals. This is known as photoelectric effect. Now, because this is a very interesting topic, before I go to the theory portion, let us quickly discuss little bit about the history of this. Okay, so this person, Rudolf Hertz, observed the photoelectric effect first in the form of sparks when when light or electromagnetic waves were falling on metals, and a lot of people got interested in that. But the next interesting development was when this guy J.J. Thomson, the J.J. Thomson used studied photoelectric effect using the cathode ray tube. Okay, and these lot of experiments were conducted, and it was found that the energy of the emitted electrons does not depend on the frequency of the light falling. It does not depend on the intensity of the light which is falling, but it only depends on the frequency of the light which is falling. And that was a bit of, I will explain all this in detail after a few moments, but it was observed that it was not the light which were the energy of the electrons which were released did not depend on the intensity of the light, but it depended only on the frequency of the light. And it was bizarre for that time, because at that time it was believed that light is a wave and not matter. Okay, at that time people did extensive studies on interference of light and diffraction of light, and it was believed that interference and diffraction can only be exhibited by waves and not by matter. So it was believed. So let us go in a little more detail. Let me explain that. So this is a metallic surface. Okay, why this is bizarre? Why that found? These are electrons, and light falls on this electrons. Okay, so these electrons basically are moving around the nucleus. Okay, they are attracted by the nucleus, and to take out these electrons, energy must be provided to the electrons so that they have sufficient energy to overcome this nuclear attractive force of nucleus. Okay, and light, it was thought, the explanation of photoelectric effect is light is which is giving the energy required to the electron. So when light hits on the electron, it absorbs the energy of the light and it gains sufficient energy to overcome this nuclear force. Now this was thought to be the explanation, which is in fact correct explanation, but the thing which was missed was, at that time, because interference and diffraction of light were observed, so it was thought that light is only wave. It is not consisting of particles or matter. Okay, so it is only wave. So if light is a wave, we know from our wave theory the energy of a wave is directly proportional to intensity I, and intensity is directly proportional to the square of amplitude. But in any case, the energy of a wave is directly proportional to the intensity of the wave. So more the light of more intensity will have more energy. So if light of more intensity has more energy, it will be able to transfer more energy to the electrons. Okay, so the electrons which is coming out, should have more energy. Okay, but that was not the case from the experiments with the cathode ray. So this is the typical cathode ray experiment, where this is cathode tube experiment, where the setup is same as the cathode ray experiments. So here on this metal surface, light typically of high energy, the ultraviolet lights are made to fall on it, and because light fall on it, it was observed from the photoelectric effect that electrons are released, and these electrons are attracted by this positive charged anode. This is connected to a positive terminal of the battery. So the released electrons are attracted to the positive charge anode. So even if without applying a very high voltage, so we saw in our last video that if we apply very high voltage, some electric sparks and discharge is there. Okay, but if high energy light like ultraviolet light is made to fall on this cathode ray, even without applying very high voltage, still there is current inside, it was observed. Okay, so now we just discussed why it was. So when they did this experiment, they found that the strength of the current, or the electrons, energy of the electrons did not depend on the intensity of this falling light. It only depended on mu, which was bizarre for that time when they believed that light is a wave. Okay, so there was a paradox here. So that paradox was solved by this. It needed a great scientist in the form of Albert Einstein to explain this paradox. Okay, and how did he, for this explanation, before I proceed further, I must mention that for this explanation he won the Nobel Prize in Physics. He did not win the Nobel Prize for his most famous theory of relativity, but he had won the Nobel Prize for this explanation of photoelectric effect. Okay, so what did Einstein say? Einstein said that this whole thing can be solved by throwing away the assumption that light behaves only as a wave. In fact, it sometimes behaves as a wave, and it sometimes behaves as particles. Okay, it sometimes behaves as wave, and it sometimes behaves as particle, and this is called wave particle duality. Okay, so any objects behave both characteristics, show both characteristics. Sometimes it shows wave characteristics, sometimes it can show particle characteristics. And for this instance, for light shows wave characteristics when it is undergoing diffraction or interference, but in the photoelectric effect it exhibits particle nature. So light or any matter, in fact, sometimes they have wave nature, sometimes they have particle nature. So in this case, light has particle nature. Okay, and like every particle has energy, okay, the light particles are called photons. Okay, light particles are nomenclated as photons. So the energy of photon is given by E is equal to h mu, where h is the Planck's constant and mu is the frequency of light. And we know that frequency can be further written as c by lambda. Velocity by lambda is also frequency. So energy of photons is given by E is equal to h mu is equal to hc by lambda. So the explanation given was, okay, the photons, now it's not the wave which is hitting this, which is causing the photoelectric effect, but the light, quanta of lights or particles of light. So these are quantas of light or particles of light or photons which are hitting. So quanta means nothing but particle. So waves are continuous. Okay, waves are continuous, but particles are quantized. Quantized means they can take only discrete values like 1 1 particle, 2 particle, 3 particle, 4 particle. Okay, so that means it can take discrete values or they are quantized. Okay, waves are continuous, particles are quantized, they can take only discrete values. So these quantas of light or photons of light, they hit and they have electrons, they hit with uh, a frequency of mu, so the energy is h mu. Okay, so they transfer the energy to electrons. Okay, so these electrons can come out only if they provide sufficient energy, which can overcome the force of attraction of the nucleus. So that sufficient energy is called the threshold energy, which is denoted by phi. Okay, so now the energy transferred by the photon is h mu. The electrons need a minimum of phi to get phi to be ejected from the surface of the metals, or to overcome the force of attraction from the nucleus. So this phi energy, okay, of the h mu which is provided, of the h mu, phi is used up to overcome the nuclear force. Okay, so the electrons, the energy of the electron when they come out of the metal surface, it is equal to the energy transferred by the photon, which is h mu, minus the minimum threshold energy, or minus the energy which is used to overcome the nuclear force, attractive force. So energy of the electron which is coming out is equal to h mu minus phi. And now we have a mathematical expression which is totally consistent with the observed experiments, which says that energy of electron coming out is not dependent on intensity of light, it is dependent on the frequency of light. Okay, so in photoelectric effect, this is an interesting topic, and also interesting topic means it is amazing to note that a particle, whether it is a photon, whether it is an electron, it can behave both, or even a proton. Okay, every particle can behave as wave also and as particles also. Okay, so in fact you are consisting of lot of subatomic particles, so you can behave as wave and as well as particles. Why we don't observe this phenomenon in real life, that is a different question to be taken later. It has something to do with our masses and Heisenberg's uncertainty principle and so on and so forth. But in general, theoretically, each and every whether it is a matter or an energy or a photon or a meson or a gluon, every particle in this universe can behave as a wave as well as particle, depending on the situation they are in, and that is known as wave particle duality. So this is an interesting topic and an easy topic also, because you need to know three things in mind. Okay, just three things. What is the three things? Energy of any a wave or of particles, photons, E is equal to h mu, and because of this implies that from photoelectric effect, energy of the electron which is released is equal to h mu minus phi. This is the first thing to remember, which was easy. The second thing to remember, which is also easy, is because it is a particle, photon behaves as a particle, electrons behave as a particle, so all these particles must also have a momentum associated with them, and that momentum P is given by h pi lambda. This formula was given by de Broglie. This is called de Broglie's principle, and Because of this, Deep Broglie also had won the Nobel Prize. So you see the importance of this topic. Lot of Nobel Prizes in this video. So the momentum of a photon or an electron is given by h by lambda, and h by lambda. So what is this? E is equal to h mu, okay, and E is equal to h mu, which is also h mu is also c by lambda. So what will be h by lambda? H by lambda can also be written as by E by c, correct? So energy divided by c. So if E is equal to hc by lambda, h by lambda will be equal to E by c. So this is the second small point or easy point which you have to remember. First is E, energy of photon is E is equal to h mu or hc by lambda, and the momentum of a photon is h by lambda, which is equal to energy divided by velocity. Third important thing is the concept of stopping potential. This is a bit of theoretical juggle. Stopping potential. Okay, so what is stopping potential? So the stopping potential can be understood by this diagram which we have. Stopping potential is related to the potential of the cathode ray. So cathode ray tube. So here what we observe that here intensity is I, okay. So the current doesn't depend on I, we have just studied this, so we can rule out this, okay. So whenever photon is falling on this high energy photon like ultraviolet rays, it releases electrons, and this electron has an energy. That energy is equal to, we just studied, h mu minus phi, correct. Now what is the energy of the electron? In what form this energy is stored? Is it in the form of potential energy or kinetic energy or gravitational energy? This energy is formed if due to the motion of the electron, okay. So the higher the energy, the higher will be the velocity of this electron, okay. So the energy of this electron is in the form of kinetic energy. So I can write this as half mv squared is equal to h mu minus phi, okay. So the electron which is released from the metal plate has a velocity v, which can be calculated using this equation, okay. And you will get lot of numerical problems also on this formula. Half mv squared, the energy of the electron, which is the kinetic energy of the electron, is equal to h mu minus phi. Anyway, it has a velocity, okay. So now we know that there is a current here, okay. How does this current vary with the potential which I apply? Okay, if I apply, obviously if I apply a large potential, the current will be large. If I apply a small potential, the current potential will be small. So let me draw a graph, okay, where I have V here, the potential which I am applying across this, and I have a current, okay. So I am plotting I versus V, okay. So what happens when V is equal to 0? When I can control this current, this potential, so that this is what this sign implies, okay. I have mechanisms to control this potential. So let me start with a zero potential. At zero potential, will there be a current? Yes, there will be a current. Why? Because the ejected electrons, because of this photoelectric effect, when light is falling on this, electrons is rejected, they have some velocity, okay. And some of the electrons will have enough energy, to overcome all the collisions and all. Because they have initial velocity, they will have some of them will have enough energy to reach this anode, okay. Because they have starting with an initial velocity, some of the electrons will always have, or most of the time, or can have enough energy to reach this anode. It depends on whether they have enough energy or not, will be depending on this formula, which is which if the energy of photon incident is big enough, okay, it is enough, So enough energy can be transferred here. So even without zero potential, some of the electrons, if the incident light has high energy, even without zero potential, some of the electrons can reach the anode, and we know that current is nothing but flow of electrons. So even with zero current, I will have some electrons which reaches, and obviously if I increase this, I will have some current, and obviously if I increase the velocity, this current will rise, or sorry, if I increase the potential, this current will rise. Why will the current rise? Okay, some of the electrons might not have enough energy to reach this. Okay, the energy of the electrons might vary depending on the frequencies which fall on this. Also, some of the electrons might go this way, some of the electrons might go this way and stop. Okay, so all those electrons which are being lost and do not directly go to anode, as I increase the potential, as I increase the positive charge here, those electrons will also get attracted to the anode, and this current will increase. What if I reduce it, I make the voltage negative? What if I make this voltage negative? Okay, I slowly start making this voltage negative. What will happen? Some of the electrons might still have enough energy, because it has mv square, half mv square. Okay, some of the electrons might still have enough energy so that they can overcome this repulsive force due to this negative electrode. Okay, so some might depending on the energy of the incident light, some of the electrons might still some current can flow. Okay, but as I increase this negative potential, okay, the number of electrons which have enough energy will gradually reduce, and ultimately at some potential V, negative potential V, the flow, no electron, it is so high now, it is just enough high that none of the electron can now reach the electrode. So in that case it will become zero. Okay, so what happens here? The current, as I make this V negative, this current will gradually decrease and it will become zero at some potential, negative potential V, minus V or V, because this is the negative side, I will just write V here. Okay, and this potential, or V naught, and this potential V naught is called the stopping potential. So this is the third concept. Again, it is an easy concept. This is the third concept which is important for this chapter. Okay, and what can I find? What is the value of this stopping potential? Yes, I can find. What? How I can find? So the energy of the electron is half mv squared. If that is equal to, okay, the energy lost by this electron when overcoming this minus V. Okay, so what is the energy lost by electron when it overcomes minus V? We know from electrostatics the work done is just equal to minus EV. Okay, V is the nothing but the work done per unit charge, so total work done is total charge multiplied by V. Okay, so I can replace this. Okay, half mv square is equal to h mu minus phi. I can also write it as h ev is equal to h mu minus phi. So using this equation, okay, knowing what is the frequency of the incident light, knowing the frequency of incident light, knowing the minimum energy required, or minimum the value of phi, the minimum potential required to overcome this, the threshold energy required to overcome the nuclear attraction, knowing this value, and we always know what is the charge of electron. Knowing all these values, we can always find what is the stopping potential EV naught. What is the stopping potential V naught when for there to be no current inside this cathode ray tube. Okay, so I think this was again a simple chapter, only 3 things to remember which we discussed now. Energy is equal to h mu, momentum is equal to h mu or h energy is equal to h mu or h c by lambda. Second thing to remember is the momentum is equal to h by mu. H is the Planck's constant, and which is equal to E by C from this equation. And stopping potential can be known from the formula EV is equal to h mu or h, and now I write hc by lambda minus phi. So this completes the discussion on photoelectric effect. See you in the next video with the Bohr's model of atom. Thanks. See you in the next video.